Hello guys, this is section 5.3, types of energy and the law of conservation of energy. This is the most important lesson for chapter 5. Let's talk about types of energy. Mechanical energy is a total of kinetic energy, gravitational potential energy, and elastic energy. Kinetic energy is energy of moving object. So energy possessed by an object that is in motion. If the object is not moving, the kinetic energy is zero. Gravitational potential energy is energy possessed by an object that are affected by force of gravity. Applies to all objects in the universe. So in other way, the gravitational potential energy is energy possessed by an object because of its position. Elastic potential energy, also known as a spring energy, is energy possessed by a material or object that are stretched, compressed, or twisted and tend to return to its original shape. Chemical potential energy, also known as energy of bonds, fuel energy or food energy, molecular energy, and internal energy, is energy associated with bonds in molecules. Radiant energy, also known as a light or light energy or electromagnetic radiation, is energy possessed by oscillating electric and magnetic fields. More about this we're going to learn later on. Thermal energy, sometimes incorrectly called heat energy, we're going to talk about heat and thermal energy. It is pretty much the same thing as mechanical energy and mechanical work. It's a difference. There's a similarities between those two. So let's talk about what is thermal energy. Is a total kinetic and potential energy possessed by randomly moving atoms and molecules. Nuclear potential energy, also known as atomic energy, is energy possessed by protons and neutrons in atomic nuclei. Sound energy and energy is possessed by a large group of oscillating atoms and molecules. Electric potential energy is in two forms. The first form is current energy, that energy that we use at our homes, is energy of moving charges. And other one form of electric potential energy is a static electricity, electric energy possessed by accumulated static charges. We're going to focus on mechanic energy on this lesson. There are two types of mechanic energy. Kinetic energy associated with the motion of the particle, EK, or potential energy that is associated with its position, the object position, EP. We're going to focus on gravitational potential energy, although elastic potential energy is part of mechanic energy also. The conversion of energy is called an energy transformation, the change from one form or type of energy to another. So kinetic energy can be transformed into a potential energy, and potential energy can be transformed into a kinetic energy. Under some circumstances, the mechanic energy, which is equal to kinetic plus potential energy, is conserved in quantity when energy loss is almost zero. Let's talk about conservative forces. Conservative forces are forces that their work on object does not depend on a path taken. Gravity, force of gravity, is one of them. So obviously the objects that are on a free fall are under force of gravity. Take a look on the diagram on the right. The speed of the cup is v initial at a height y initial, and its speed is v final at a height y final, which is independent from the path taken on two heights. So no matter how what you threw that cup, either straight up at a certain angle or in a form of projectile, when it reaches the maximum and comes back to the same level as it was on a first or a second. However, one thing is for sure, speed, not velocity, speed on a first case and second case and fourth case is the same. And a speed, as long as the speed on a first, second, and third is the same. So we have seen this type of thing before when we study projectile motion. We know that at the same level, you have the same magnitude of velocity, but magnitude of velocity is just a speed. So in a diagram on a bottom right, if the car has to move from level A to a bottom level, level B, no matter the path taken, either straight down or at an angle, or actually in a circle or a zigzag, that is going to be exactly the same when it reaches the point B, at level B. So that means that conservative forces do work on an object, so their speed, it is independent from path taken. Let's do a practice. Suppose that 0.120 kilogram cup is thrown straight upward with a speed of 7.85 meters per second, and the frictional forces can be ignored. So air resistance can be ignored. Use kinematics to find the speed of the cup when it has risen 1.18 meters above the fling point. So what is given is V initial Y, 7.85 meters per second. Mass is 0.120 kilogram. Delta Y, so the height is 1.18 meter. What is required is a final speed at that point. So magnitude of velocity. We can use kinematics to solve that magnitude of velocity or speed at that level. So V final Y square is equal V initial Y square plus 2AY delta Y is equation number 4 of kinematics. Now we can solve for V final, which is a square root of V initial Y square plus 2AY delta Y. And you plug numbers there, and you're going to get 6.02 meters per second. The second one is, point B, is show that total mechanical energy, which is kinetic energy and gravitational potential energy, of the cup is unchanged. So total energy is equal to a gravitational potential energy plus kinetic energy. Gravitational potential energy at initial point is mgy initial, and kinetic energy on initial point is half of the m v initial square. Okay, let's see. Now, gravitational potential energy at the point 0 is a reference level. It is 0 because height, relative height is 0. Now, for kinetic energy, is initial velocity or initial speed per se is 7.85 and mass is 0.120. So you can plug those numbers in the calculator and you get total energy at the initial point is 3.70 joule. Now you can do the same thing for final point. So final point is gravitational potential energy at the final point plus kinetic energy at the final point. One more time, gravitational potential energy at the final point is mgy final, and kinetic energy of the final point is half of the m V final square. Then you can plug numbers there, and you're going to get a total energy at the final point is 3.70 joule. And you see those are exactly the same. So now total energy at a point 0 is equal to a total energy on point final. Initial and final total energy are the same. So scientists study the energy transformation that led to a low conservation of energy. So while they are studying energy transformation, they notice that when one form of energy transforms to another form of energy, the quantity of one form is reduced, and the same way, the quantity of the other type of energy is increased. This suggests that energy transformation, the total amount of energy does not change. So total amount of energy remain constant. For example, you have a light bulb. Light bulb, especially incandescent light bulb, that have two type of energy that you can noticeably feel it. So total energy is electric energy that is used to light the light bulb. It's going to be a light energy that you see a light out of it, and thermal energy. How do you know it? You touch the light bulb and it's hot. So thermal energy is part of the energy transformation. So not all the electric energy is transformed to a radiant energy, light energy, but thermal energy is a part of it. As a matter of fact, there is another very small type of energy, which is a sound energy. But because it's too small and you cannot really hear much of that sound when the light turns on, especially when it's incandescent with a filament, then radiant energy and the thermal energy are those two major energy transformation. More about this we're going to learn on efficiency. So here is the law of conservation of energy. Law of conservation of energy states that total amount of energy in the universe is conserved. So it's a certain amount of energy in the universe, and that total never change. So new energy cannot be created out of nothing, and existing energy cannot disappear. The energy that exists can only change from one form to another. So when energy transformation occurs, from transforming the energy from one form to another, no energy is lost. Yes, this is an ideal situation, but this is what we're studying. So energy conservation happens when total energy before is equal to total energy after. We can express it differently as a total initial energy is equal to a total final energy, or total energy at point 1 is equal to a total energy on point 2. And we're going to use those to solve problems. Let's analyze the energy transformation of an object falling from position A to D and see that what would be total energy at point A, at point B, at point C, at point D. Let's start with a position at point A. Total energy at rest, position A, is labeled as ETA, total energy at point A. So at point A, we have two things. The height is h, and speed at point A is 0, because it is at rest. So we can say total energy at point A is equal gravitational potential energy at point A plus kinetic energy at point A. So gravitational potential energy at point A is mgHa, and kinetic energy at point A is half of the mVa square. Now we know that VA is 0, so that will simplify things, and total energy on point A is mgh. Now let's do a total energy halfway through. At position B. We choose B to be halfway through because it's easy to use kinematics to find what would be speed at point B. So total energy at point B is equal to a gravitational potential energy at point B plus kinetic energy at point B. So we are consistent with formulas. We're using exactly the same as at point A and exactly the same at point B. So what we're looking is the total energy on point B is the gravitational potential energy on point B. So we know mg and hb, which is half of the h. And kinetic energy on point B is half of the m vb square. But we don't know speed at point B. That's why I just said we use the kinematics to find what would be speed at point B. So vb square is equal va square plus 2ay delta d ab. Now, ay is g, and displacement from A to B is another half. So B is at half, so H is the total, so half is left for displacement from A to B, half of the H. So that will simplify things because we can say VB square is equal VA square plus 2GH divided by 2, so half of the H. Now, for more, we can get rid of VA square because it's 0. Now, what's left is VB square is equal 0 plus GH because 2 and 2 cancel. And speed at a point B square is equal G times H. Now we can actually substitute GH where the VB square is. And we have total energy at point B is equal mg h over 2 plus half of the mgh. So that means half plus half would give you the total mgh. So if you see that total energy on point A is mgh and total energy on point B is mgh. But let's see what will happen at point D. So what would be a total energy at bottom just before it hits the ground? So at position D. We label it as total energy at point D. We know that total energy on point D is equal to gravitational potential energy at point D plus kinetic energy at point D, as always. And we can replace what is gravitational potential energy at point D is mg delta H, which this case is HD. And kinetic energy at point D is half of the m Vd square. Now we don't know speed at point D, so we can use the kinematics to solve for Vd. So Vd square is equal Va square plus 2ay delta d between A and D, which is H. We know that V at point A is 0 because it is at rest. So what is left is Vd square is 0 plus 2gh. So Vd is 2gh. We replace Vd with 2gh, and we know that D is 0 because it is at a level point. It is at a bottom level. So we can replace that mg delta H with 0, and we replace Vd square with what Vd square is equal, is a 2gh. So we now 2 and 2 cancel. Total energy at point D is equal to mgh. So we can summarize this. We can say total energy on point A, which was mgh, has to be equal to total energy at point B, which again is mgh, and equal total energy at point D is equal to mgh. So the total energy at point A, at point B, and at point D is conserved. We can do the same thing for point C, for any point in between. But you got the point. Total energy at any point between A and D is conserved, so it's equal to total energy on each individual point between A and D. If you analyze that, total energy at point A was just gravitational potential energy. As the total energy at point B became as a half gravitational potential energy and a half of the kinetic energy, then you see that kinetic energy increased while the gravitational potential energy decreased. As we move along, we can surely say that total energy at point C is going to be less gravitational potential energy and more kinetic energy. As you know, as the object moves from point A to point B to point C from kinematics, it will speed up. The speed is going to be bigger. So the kinetic energy is going to be bigger. And at the bottom, when it reached the maximum maximum speed, kinetic energy will be maximum, and since that is at the reference level, gravitational potential energy will become zero. So we can say that energy that exists can only be changed from one point to another. So we can conclude that total energy on point A is equal to total energy on point B, equal to total energy on point C, equal to total energy on point D, and any point in between. So the energy is transformed from one form, which is a gravitational potential energy, to another one, which is kinetic energy. So as gravitational potential energy decreases, kinetic energy will increase, but as a total, never change. What would be a theory without practice? Really nothing, because you're going to forget it tomorrow. So let's enforce that understanding using one typical example of law of conservation of energy, pendulum. So pendulum is going to go from point 1 to point 2, and then it's going to continue on to point 3, go back to point 2, and point 1 again. So it's going to start from rest at point 1, and it's going to go and reach the maximum speed at point 2. So let's write what is given and what is required, and law of conservation of energy formula as well. So what is given is angle 45, length is 3 meters, speed at point 1 is 0 at rest, and what is looking for, speed at point 2. Remember, we are in an energy section, so we use energy formulas to solve problems. So that's what we are going to do, using energy conservation formula. Total energy at point 1 is equal to total energy on point 2. That is the very start of the solving problem, because we're using law of conservation of energy. So what is total energy at point 1? And what is energy on point 2? Total energy on point 2. Gravitational potential energy plus kinetic energy on point 1 is equal to gravitational potential energy plus kinetic energy on point 2. So what is gravitational potential energy on point 1? mgh1. And kinetic energy on point 1 is half of the mv1 square is equal to mgh2 plus half of the mv2 square. Now, to simplify things, if you see mass is not given, and on purpose is not given, because we don't really need mass. Mass is the same on both sides of the equation, so you get rid of it. And to make it easy, you just multiply by 2 to remove those halves as well. So we get 2gh1 plus v1 square is equal to 2gh2 plus v2 square. So now we can solve for v2 square, which is v1 square plus 2gh1 minus h2. So we can factor 2g because it's common on both components. So on a 2gh1 and 2gh2. So you are moving 2h2 on other side of the equation become negative. So that's why we have the formula of v1 square plus 2g and h1 minus h2. Now, v1 is 0, so that simplifies things. So what we're looking for is difference between h1 and h2. So we square root it of 0 plus 2gh1 minus h2. So we have 2 points here, h1 and h1 at this point here and h2 at this point here. So, but we are looking for difference between h1 and h2. And difference, we label it as a delta h. So v2 is equal square root of 2g delta h. So, but how can we calculate delta h? If you take a look, the length from this point here, which could be a point 0, is equal from point 0 to 1 is equal to a point 0 to 2. So this one actually is L. Now, if you look at this triangle, it's a right angle triangle with a hypotenuse of L. Now we can say the delta H is equal L, which is the long one, which is the length of the pendulum, minus what is here, this length. This length here is adjacent for this angle. And you know that adjacent is equal hypotenuse, L, times cosine of that angle. So L cosine theta, which is cosine of 45. And then we can continue, because we do have L is 3 meters, and L cosine, and we have theta, which is 45. Then we can solve it. Delta H is 0.88. And next step, you go to that formula here, and you can replace delta H with a 0.88, which is giving us as 4.14 meters per second. So we know now the speed at a point 2 is 4.15 meters per second, which would be the maximum speed. How do we know that? We know that at this point here, H, at this point here, at this reference level, this pendulum cannot go lower than that. So that would be 0. That would be the lower position. At the lowest position, gravitational potential energy is 0. So everything is turned, is converted, is transferred into kinetic energy. So maximum gravitational potential energy here. How do we know that is a maximum gravitational potential energy? Because kinetic energy is 0, because V1 is 0. Now here, we know that is at the lowest point, cannot go lower than this because its strength does not allow it to go lower than this. It is where the gravitational potential energy becomes 0, and a total energy will become a kinetic energy. That means that is a maximum speed possible because mass doesn't change, mass is the same. So V2 is the maximum speed, which is 4.15 meters per second. Let's do a roller coaster practice problem, which is a typical problem for a low conservation of energy, because we have here gravitational potential energy can be transformed to a kinetic energy, and kinetic energy can transform to a gravitational potential energy at that other point. So let's start with a roller coaster begins from rest at a position A. Calculate the speed of the roller coaster at position B. So what is given here from a diagram is HA is 54 meters. Speed at a point A is 0, start from rest. HB is 15, and what we're looking is VB, speed at point B. We can write the conservation of energy formula because we are in an energy section. Please do not use kinematics formulas. Although you can solve the problem with kinematics, do not use in this section. Low conservation of energy is total energy on point A is equal to total energy on point B. So what is total energy on point A? Gravitational potential energy plus kinetic energy on point A. And what is total energy on point B? Again, the same. Gravitational potential energy on point B plus kinetic energy on point B. We can write what are those formulas equal to. So mgHa is the gravitational potential energy on point A. Half of mVa square is kinetic energy on point A is equal to mgHb is gravitational potential energy on point B plus half of the mVb square, which is kinetic energy on point B. Now, if you look, m is everywhere. You can factor and cancel it. And to make it easy, you can multiply by 2 and you get an easier formula there as a 2gHa plus Va square is equal to 2gHb plus Vb square. Now we're looking for Vb. So you can isolate a variable. Vb square is equal to a Va square plus 2gHa minus, we move that 2gHb to another side of the equation and becomes negative. So minus 2gHb. Now there are two things that we can do here. We can get rid of Va square because it's 0, start from rest. And we can factor 2g because it's the same on a both. And then we have Vb square is equal to 0 plus 2gHa minus Hb. For next step, we do square root it. So Vb is equal to square root of 2gHa minus Hb. And now we are ready to plug numbers. So we have 54 for Ha and 15 for Hb. Then we have speed at the point B is 27.65 meters per second or 27.7 meters per second. B, calculate the speed of the roller coaster at position C. So what is given there is height at the point A is 54 as previous, V at the point A is 0, and height at the point C is 47, and what we're looking for is V on speed at a point C. Now, we could have used B and C. So total energy on point B equal to total energy on point C. However, I always say this is not recommended. If you have choice, you always use given values. So VB is already calculated value from A. So it is recommended not to use it because if you made a mistake at A, that will carry now the mistake at B. So what we do, we keep 2 points. The first one, which has both given, and point C, which we have one given, H47, but C is that what we are looking for. And again, you use only conservation of energy formula. Total energy on point A is equal to total energy on point C. And what is total energy on point A? We'll already know is a gravitational potential energy plus kinetic energy on point A. And what is total energy on point C? Gravitational potential energy and kinetic energy for C. And we can write, if you see that we use exactly the same step, don't skip steps because it's very, very recommended to use those steps and you'll never make mistake. Masses are everywhere the same. You cancel it and you multiply by 2 and we have a simple one. 2g HA plus VA square is equal to 2g HC plus VC square. We're looking for VC, so we can isolate the variable. VC square is equal to VA square plus 2g HA minus 2g HC. We move that 2g HC from another side of the equation, and then we have VC square is equal to 0 plus 2g HA minus HC. Now we can solve for VC, which is square root of 2g HA minus HC, and we have all what we need. VB is equal to square root of 2 times 9.8 meter per second square times difference between those two heights, 54 minus 47, and we have VC is equal to 11.7. If you see, the speed decreases, and it's common sense because height increases. Gravitational potential energy increased. So now that gravitational potential energy that was increased was taken from kinetic energy. So total is the same. Imagine this as no friction and no air resistance. So that's what we're talking about in an ideal situation. Total energy in point A is equal to total energy on point B is equal to total energy on point C. However, there is an energy transformation from gravitational potential energy on point A to both kinetic energy and gravitational potential energy on point B, and on a C is a gravitational potential energy and kinetic energy. However, if you compare energies at point B and energies at point C, although total are the same, at B we have more kinetic energy because it's faster, because we have a less gravitational potential energy because height is smaller, compared to C, which we have more gravitational potential energy because height is bigger than 15. Obviously, the speed is going to be less than speed at point B. Here's another practice problem. A player hits a 0.15 kilogram baseball with a speed of 36 meters per second and the fan catches it 7.2 meters above the point where it was hit. Neglect air resistance. So, law of conservation of energy applies. What is the kinetic energy of the ball when it's caught? So what is given is a mass of the ball, 0.15 kilogram, height relative to where it was hit is 7.2 above that line, a reference line. Speed at point 1 where it was hit is 36 meters per second, and kinetic energy is required. So the height at the point 1 is 0 because it was the reference point when you refer to H2. Now, law of conservation of energy applies. Total energy on point 1 is equal to total energy on point 2. Then gravitational potential energy on point 1 plus kinetic energy on point 1 has to be equal to a kinetic energy and gravitational potential energy at point 2. Now we are looking for kinetic energy at point 2. So isolate that EK2, which is equal to gravitational potential energy on point 1 plus kinetic energy on point 1 minus Eg2, which we move that to another side of the equation, then becomes from positive to negative. Now, as I said, height of the position 1 is 0 because that would be as a reference level to say that is H2 is 7.2 meter. So what we are left with 0 plus kinetic energy on point 1 is half of the mv1 squared minus gravitational potential energy on point 2 is mgh2. So we have everything now to solve for EK2, which is half of the 0.15 kilogram times V1 is 36 meter per second, all in power of 2, minus 0.15 kilogram times 9.8 meter per second squared times 7.2 meter. And if you plug those in your calculator, you'll get 86 joule of energy. B, what is the speed V2 of the ball when it's caught? Now, this is a typical problem when we have no choice. We can use whatever is calculated values on A to solve for B. So we have mass that is already given, and we have calculated values EK2 in order to find V2. So formula for kinetic energy is half of the mv squared. Then we can solve for V2 squared is equal to EK2 divided by m, square rooted. Then we plug numbers. So EK2 is 86, we already just calculated it. Mass is already given, 0.15. That equals to 34 meter per second. So I hope that you enjoy it. I hope that you learn something from it. And that concludes the lesson for today. Until next time, have a good one.